Thank you. I'm a trained architect, but I'll show you a bit how we can import and transfer all kind of interesting technologies into architecture and develop a much more performant built environment through these technologies. So I'm presenting work from our institute group at Stuttgart University, headed by Professor Aachen University. So it's really, I'm privileged to work with that colleagues. So our focus is on computation and materialization. And that's always the question in architecture. Usually someone draws a shape and then someone else sees how it gets built. We are more interested in the interrelation between those two. So how can the later materialization inform the fabrication process from the very beginning? And there's a certain historic precedent of that in Stuttgart, which is Frei Otto. The interesting thing is here how such a soap bubble, for example, the shape is emerging through a set of boundary conditions that generate this material performance informed shape. That is not, like, the very interesting distinction is that this is not drawn by a designer, but it's really developing out of a meaningful negotiation of boundary conditions that Frei Otto then used to transfer that to cable net constructions, for example. So we think with current technologies it's very interesting to revisit this train of thought. And usually in architecture you see a serial production of parts that get added into a building. But if you look into how nature generates shape and materializes it, it's done in a much more integrated way. So, for example, you have the processes in nature allow to have very localized, differentiated geometries, which is often not the case in architecture, but is nowadays facilitated through new technologies that we can introduce this into architectural construction and design processes. So, for example, in nature you achieve a much more functionally integrated way of achieving certain functions, and also a much more material efficient way of achieving functions. So we see how can we transfer this into an architectural design and production process. And therefore use a very integrative design method where computational design technologies are at the center and bring all of these from the design to the fabrication process. All these things are simultaneously fed into the design process from the very beginning. We realize these structures in a one-to-one scale. Those are research prototypes produced at Stuttgart University in a multidisciplinary cooperation with biologists, structural engineers, material scientists. And it's very important to test these things on a one-to-one scale because a lot of interesting aspects that you, for example, find in natural role models are difficult to scale, and so you only see if it works when you get to a demonstrator scale. The interesting thing is also architectural pavilions have always served as a role model for the push of a specific research aspect, but you can leave some requirements that are usually in the game when you design a functional building away. So those are highly efficient, lightweight constructions. We're currently investigating, for example, facade technologies for this as well. So really like a bottom-up exploration where we reshape the fabrication and design strategy from the beginning. When we look into nature, you see a lot of complex forms. But similar to the soap bubble, these are not like merely playing around, but those are really developed out of certain interrelations between the functions and the material they are built out of. So we're looking into complex morphologies that are informed by their function and their surrounding. The second aspect we're interested in is the material layup. So what you saw before was a pincher claw of a lobster. It's made of a fiber composite. And the interesting thing is that you can achieve a highly differentiated structure with these kind of things. So the lobster has very soft elements and very hard elements to its shell. This difference in material properties only is emerging through different orientation of the material. Furthermore, functional integration, I mentioned that before. It's not only a highly efficient shell structure on the lobster, it's also mediating internal, external climate and all kind of conditions that need to be negotiated between the organism and its habitat it's living in. That's a general principle. Wood has cellulose fibers. We have collagen fibers. So a connective tissue, like a soft, squishy thing, is the same material like a tendon, which is a very linear construction element for tension forces. It's just about how you organize this material. what does that mean for the architectural design process? We need to start our design on the material level. We need to have control over how we can arrange such a fibrous material and therefore tailor our own structural material system. We transfer that into technology through fiber composites, which have been used in aerospace construction and transportation engineering for quite a while. You have fibers, and they're embedded in the polymer matrix. How they're used in industry is a different thing. You can't just transfer these principles into architecture, especially not when you want to follow the path of these very differentiated structures we saw before in the natural raw model. Because here, there's a elaborative formwork involved. Yeah? And that bounds the actually very formable material back to a serial production logic, because you have the economics behind of once you have to generate this really expensive form, and then you can just serial produce the same part. What we want to have unique parts with unique geometry and unique fiber layout and structural properties. So in our first investigation, we saw how can we achieve that. And you see there's like biologists involved and industry support. So it's a very interdisciplinary undertaking, and the computational design processes can really form this point of confluence where all these influences from various disciplines are integrated into the design process. So we developed a fabrication strategy where a robot places fibers onto a very minimal form, which in industry usually that would be milled out of foam, and then you have several surface finishes. So basically you already built your building as a formwork before. Then of course you can pull out multiple times. But what we're doing here is we place fibers in a way that they interact with each other and generate the shape through the material interaction. So you need to think about a line that spans across space. When you have a certain one pressing against it, they reciprocally deform each other and generate an interesting curvature that we can then utilize for the structural behavior of this thing. That is not only a very material efficient way of construction, but it also expands the architectural design repertoire. So the interesting thing is if you transfer robotics from, let's say, car industry, where it's used since a while, if you transfer composite materials from aerospace, where it's used since a while, and combine those and apply that to architectural construction, you not only achieve a lot of material savings, but you also expand the design repertoire that architects can tap into. In a follow-up project, we developed a doubly layered segmented shell from that. So here we had two collaborative robots, and you see there's no formwork in between. We had a reconfigurable frame that allowed us to fabricate 36 different building components, all with different geometry, different fiber layout, and there's no formwork involved. It's one process that we want to set up, and then we can get the whole differentiation and adapt each element locally for its structural requirements to use the minimal material that's used to stabilize the structure. And again, it also transfers a very interesting material characteristic. So these shapes and patterns are all emerging through a meaningful interaction of the aims and boundary conditions and processes that are underlying, but also add a really rich detail and material characteristic to the outcome. I want to talk about this project a little bit more in depth, which is the recent research prototype that we produced together with the Institute for Structural Design at Stuttgart University. And also together with our master students. So those projects are really at the boundary between research and teaching, and our master students really contribute big parts to this. Before we were looking into fiber arrangements and morphologies, performance morphologies and biological structures, and transferred into the lightweight construction system. This time around, we chose a very different approach to the biological raw model, and we looked into behavioral strategies. How does nature form fibrous structures? And coming back to the formwork issue before, how can complex forms be achieved without using a lot of material to generate this form in the beginning? So this is the water spider, lives its entire life underwater, still needs air to breathe, and stabilizes a water bubble with a fibrous net it spins around. So we thought that's a very interesting process to look at. And we had several spiders in our basement, and there's a very interesting procedure to how the spider manages to build this very stabilized form, even if you vary the boundary conditions. We tested all kind of different currents. We cut pieces away, so it's a very robust nest that comes out in the end. And that was then interesting for us as architects again. Like there's a very complex fibrous morphology emerging through this process that we saw as a potential to be used for architectural construction. And it's a very material efficient way of generating such a shape because there's no underlying formwork except the air bubble, basically. So again, the material level is also very interesting. Hierarchical organizations, fiber spreading, bundling, locally reinforcement, all these things can be abstracted and then transferred into a computational design strategy. What we pulled out of this is two aspects. One is the air-supported formwork. So we just had a very thin membrane that's supported with air, so there's the least material possible involved to define this shape. And then there's a behavioral design strategy to organize those fibers according to a various set of boundary conditions. So I mentioned before that those are very integrative design processes. So robotics, the biomimetics, structural considerations, all of that needs to be integrated into the design process. And we did that, for example, by looking into the robotic kinematics. Where can the robot reach the space? Where is the structure loaded the most? And then fed this information into an agent-based design process. You can imagine there's a point running across the surface, and it makes decision every time it moves based on several layers of information that are overlaid. And therefore, there's this fiber arrangements emerge through this process. So the agent actually manages to negotiate all these boundary conditions. It's not a structural process how you usually optimize towards one aspect, but it's more negotiating a certain set of boundary conditions. Where can the robot reach? Where do we need the fiber structurally? And again, that also offers a lot of design potential. So you see there's various options. It's also very interesting to see how you automatically articulate certain aspects. So the agent reads the stresses. It reinforces the entrance, for example, in a certain way. And also the transparencies. So you don't have opaque wall and the window, but you have gradients between denser structural reinforcements and more transparent things. Then, what is very important in such a process is the prototyping. So we're prototyping processes. There's no standard way how industry does this. So we always need to come up with a solution by ourselves. So that was an early test. How can I glue a carbon fiber onto such an ETFE membrane? There's certain problems with that we need to overcome. But the interesting thing is how designing your own tools as an architect becomes an integral part of the design process itself. It's not a mere technical task that you need to solve, but it's really something that defines your design outcome to a large degree in the end. So later, and that leads to an interesting conceptual difference to the previous project as well, where suddenly, based on these findings from the prototyping of the process, we had to integrate a lot of dynamic features, like the membrane was deforming, for example, and we fused the agent I showed before with the actual physical fabrication. That's what we call the cyber-physical fiber placement, where the agent really fuses with the robot, and the robot makes the decision on the fly while he's laying the fibers. So it's not that we program the robot and it's merely executing a task, but it's aware of its environment. It takes decision while it's fabricating. That involves an elaborate tool that has sensors embedded that regulates the amount of glue, the amount of fibers, the pressure that the tool applies. So that's really the fusing of the physical and the digital. We inflate the formwork, and the robot places the fibers on that formwork. You can see that here. So the entrances are still enclosed. The thing is air supported and then subsequently turns into a stiff composite shell. What does it mean in the end for architecture? It's not, I mentioned that before, not just a technical challenge that we managed to resolve, but it really allows ourselves to, for example, here we went one step further. The formwork is now an embedded facade system, for example, as well. The ETFE is a building-grade material that's used in stadiums. So we have a very lightweight construction. So the whole thing weighs 250 kilograms. It's around 50 square meters. So we have a construction weight of 5 kilograms per square meter. That's ultra lightweight construction, and ultimately allows you to save huge material savings in building construction on the horizon. And again, not only a technical achievement, but also the characteristic of that is very interesting. It generates a really interesting space. The material haptic is interesting to experience. And you have this rich pattern that's not a mere design feature, but really outcome, like it's really developed bottom up through the processes itself. You can find more interesting projects on our institute webpage. There's various also wood projects, fiber composite projects. You can check it out. Thank you.